Test, test. Okay, we will be starting now. So, welcome everyone to this week's PhySU Colloquium. Akash will be talking about open quantum systems. Let's give him a warm welcome.
Mic's on? Okay, great. All right, hi everyone. I'd like, if you've taken a quantum mechanics course, think back to probably last day of class, so your first course. It's almost exam time, maybe you're getting a little stressed, and then your professor says, today we're going to solve the hydrogen atom. And you run through a bunch of PDEs, and at the end you say, voila, look, I've just found the orbitals of hydrogen are the solutions to the time-independent Schrodinger equation for that. And you say, well, that's pretty cool. That's took a lot of work, but we got a pretty cool result. And then you pause for a couple seconds. You say, something a little off with that. Because the hydrogen atom, apparently, you've just shown that its excited states, its 2p, 3p, and so on orbitals, are steady state solutions to the Schrodinger equation, which would say that they would live for an infinite lifetime. Yet you know that atoms decay, you know excited states decay to the ground state. So something's off. And then maybe you do a little more introspection and you realize, wait, I never included photons in my theory. I just wrote a proton, electron. I have no way for emission processes to occur. And so you'd say, well, really, I've solved the hydrogen atom modulo how it interacts with its outside environment. Let's say instead you're trying to study a chemical reaction. So you have, say, a sodium ion dissolved in 10 to the 23rd water molecules, and you're studying its dynamics. And you say, well, I could treat the sodium atom like it's in a vacuum at 0 Kelvin, or you could say it's going to have some non-trivial energy exchanges with its surrounding molecules. And you could ask, how is that going to affect it? Or maybe, you've been reading a lot about quantum computing, and you know that IBM puts their big fancy computers into giant fridges, and you think, oh, right, the world does not like isolated quantum systems. Quantum systems are not just this ideal picture of a system unable to see anything else. Fortunately or unfortunately, depending on what you're studying, they interact with the outside world. And that's really the field of open quantum systems, is trying to understand how can I systematically study the way a quantum mechanical system interacts with its environment, and what new phenomena and what new paradigms do we see that we wouldn't have seen if we just thought of everything as isolated. That's the goal today. I don't want to get into too much of the mathematical details. Today, instead, I'd like to try to illustrate a lot of the big picture ideas and big concepts of this field, and hopefully get you a little interested in it. So first, I want to say the goal for today is I'm going to hopefully start by convincing you that open systems are actually nothing new. You've been doing them for much longer than you've actually been studying physics. And then we'll try to see actually how we try to apply classical logic is going to break down when we study a quantum mechanical system that's open. And so we'll have to actually introduce the idea of density operators and see how entanglement actually messes up how we want to actually study this thing. And then we'll try to study how does a density operator behave, and what does that mean about how actual systems behave. And maybe if we have time, we'll try to end with talking about how do you get statistical mechanics out of this, how do you get non-equilibrium statistical mechanics out of this, and so on. So I'd like to start with a very elegantly drawn diagram I have here of just a block moving on a rough surface. And you kick it with some velocity v, and you ask, how does that behave classically? If I kick it and I let it go, what happens to the block? Just classical mechanics. It moves, yeah, but beyond just moving, if it's a really rough surface, can you say anything about how it's going to behave? Right. Yeah, but what you said there is very interesting. You said due to the coefficient of friction, which is a very interesting way to put it, because you've said that you are going to attribute the fact the block slows to a friction force acting on it. But really, you could do instead, because we studied a lot of physics, we know electrostatics, we know Newtonian mechanics. We could say, well, this surface is actually made of a lot of molecules. And so we could think about all the little electrostatic interactions between the molecules in the block and the molecules in the ground, and we could solve a big F equals ma problem for them. And so we'd say, okay, we could say, really, I need to talk about a block but I also need to talk about atom 1 in the ground, atom 2 in the ground, and so on, and then you'll end up with 10 to 23 atoms in the surface, roughly. And so you could solve F equals ma for this, and then at the end you'd find that actually the net force on the block from all the interactions with the surface is actually just this friction force. And that's a perfectly valid way to do it. But you tell me that that's kind of a wasteful, and that's a little bit unnecessary, because it seems like a lot of work to keep track of 10 to the 23 molecules all interacting with this block if at the end of the day all you want to know is, does the block slow down? It seems like, and as you pointed out, you can just say there's an effective friction acting on it, and that's what slows it down. That picture, I'd argue, is a lot more physically insightful. It's also a lot simpler mathematically. You can just plug in into your favorite kinematic equations instead of having to actually keep track of billions upon billions of positions of particles. So that kind of gives us this idea that if I'm studying a system, even if it can interact with other things, often you want to instead of describing everything with perfect resolution, like describing every position of an atom in a block, you often want to just go for an effective description, because that's going to get you the answer you want. It's going to tell you the information you need without necessarily complicating things with every little detail you may or may not care about. And so in classical physics, it's actually not that hard to do this. I just ignore everything else. Because if I know, whether phenomenologically or theoretically, that there is some effective interaction from friction, then I don't actually need to track this. I can just say, replace this theory of 10 to 23 particles with a theory of one position of a block plus some friction force that accounts for how the environment influences it. And notice that in the classical world, this is actually not a problem, right? Because I'm able to talk about the block's position independently of the molecule's positions in the surface, it's not actually a big conceptual leap to switch from a big description of the entire universe to a reduced description of a single subsystem. So in that way, Newtonian mechanics is actually very well suited for open systems. You just focus on a smaller set of variables, and you add an effective interaction describing whatever you've removed from your theory. So the goal now would be that replace the block with something quantum mechanical, replace the surface with some quantum mechanical environment, and try to do the same thing. Try to isolate certain descriptors or certain variables we care about studying, and try to, instead of doing a really detailed description of all the interactions, try to give some effective idea. And so you might want to guess, maybe that's not too hard. Maybe I just do what I did with the classical system. So let's say, I'll move this over here. Let's say we go back to the example of this sodium ion moving in some solvent of water, and let's treat all the water molecules quantum mechanically and the sodium ion quantum mechanically, so we'd have some very, 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 very big wave function we want to study. But we say, oh, I actually only care about some chemical reaction the sodium ion does. I don't really care about how the water distributes itself, so I just want to study how the sodium's behaving. And so we'd say, I'd like to just, instead of describing every fine-grained detail of the water, just describe the sodium and get some effective effect of the water on it. And so maybe we could define some effective Hamiltonian describing the system as perhaps I'll put a big question mark here because we don't know yet, but maybe just some internal Hamiltonian for the sodium. It's all the Coulombic interactions within it, plus some friction term, maybe. That would be the analogous guess to describing a classical system by adding an effective force. Maybe we can add an effective Hamiltonian that describes it. But the problem actually comes in when we try to even talk about the sodium atom on its own. Because if you've heard anything about quantum entanglement, you know that the big surprise, the big takeaway of that is that in the quantum mechanical world, when systems interact, you can't describe one piece individual from the other. You can only describe the collective whole if you want to describe it as a wave function or a state vector. So suddenly, that step we had before where we just removed everything else and only focused on one coordinate is a lot less trivial. It's not built into quantum mechanics. Suddenly, we're not going to be able to do that as easily. And so this idea that maybe we can just describe the system as some normal quantum mechanical problem with some effective interactions is not going to actually work out very well. And so I want to actually illustrate what happens, what goes wrong with trying to describe it as a what we call a pure state, or a like kind of what you're used to from quantum mechanics, just a state or a wave function, with just kind of an example. So let's say we've split our system into what we call our system and what we call the bath, or the environment. So in the sodium example, it would be the sodium ion, and the bath, or the environment, is all the water molecules surrounding it. And maybe we say the whole system is entangled because of interactions between water and sodium, and it's described by some state that looks something like this. It's kind of your typical entangled state, where the first vector is describing the sodium, the second is describing the state of all the water molecules. And then I'm going to also say, just for simplicity, that these states are actually orthogonal to each other. Now our goal is to get from this description of a system plus its environment, which is in practice, if you actually wrote this out, would be some very, 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 very high dimensional system, to a much smaller reduced description of this system alone. And in part of that, we want to be able to recover any statistical properties, any expectation values, because at the end of the day, we want to predict things. So you might look at this and you might say, how would I describe the subsystem 1 alone? And maybe a good guess would be, maybe it's this. Maybe subsystem 1 can be described as just psi1 plus psi2 over root 2. Because it looks kind of similar, right? You have psi1, psi2. Let's just cover up these pieces and call it a day there. Maybe that will work. And so we could consider then some operator S that acts on the subsystem alone. So maybe we're measuring momentum or angumentum or energy of the sodium atom on its own. And we could say, well, we better have that the expectation value we get from applying it to state T would be the same as what we get from applying to state T prime. Because the goal of our reduced description with state T prime is to recover everything you get by describing the full system without having to worry about keeping track of every little particle in the solvent. But if you actually compute that out, we can start with T prime. T prime, this is kind of just your standard quantum mechanical calculation. You'd get a half of psi1 s psi1 plus psi2 s psi2 plus 2 times the real part of psi2 s psi1. And then from quantum mechanics, you'd say, right, I can see that the expectation value for a superposition is, first you have terms that look like what you get from system 1 on its own, system 2 on its own, but then you have some interference term between the two pieces, right? This is, it's the whole idea that you sum before you square versus you square before you sum. Interference is this quantum mechanical thing that means that suddenly superposition is not just simply taking 50% chance of having these. There's something else going on here. And so you would hope that maybe T would look the same, but if you actually work through T, you only will get that it's psi1 s psi1 plus psi2 s psi2. And that comes from the fact that when you have the cross terms in those cases, the fact that these environment states are orthogonal ends up meaning that they don't contribute anything. And so this is kind of interesting because suddenly it seems like, well, first of all, we know that our guess was wrong, right? These are not equal. So this state T prime is not a good reduced description of our state T. But we also notice that it seems as if the effects of quantum entanglement or of quantum superposition are completely gone. There's no more interference. Instead, I just have a 50% chance of having the values I get for being in state 1 plus the 50% chance of having the values I get for being in state 2. So it actually looks a lot less that I have a quantum superposition, but rather I have something that looks like you'd say probability of being in state 1 is 50%. Probability of being in state 2 is 50%. instead where I just don't have enough information to say, am I actually in this state or am I in that state? And so and it turns out more generally that yes, any open quantum system, because of the way a system entangles with the environment, you cannot describe the system alone as a well-defined vector anymore. Instead, you can, at least statistically in terms of recovering all expectation values, all measurement results, you can describe it as a collection of vectors with some chance of having each one. And so this is kind of the paradigm in which we want to go forward, in which we want to study basically what states do I have in my ensemble or my collection of vectors, and how are these probabilities of having different ones changing? And that will be, we're going to want to see how that evolves in time and how that behaves, and that would end up telling us, for example, how does that sodium ion react? Does it react? How does it exchange energy, and so on? But it would be a little bit clunky if we had to keep this description of study one, study the other, and then weight all their averages. So what we want to do first is we want to come up with a better way to treat these ensembles of quantum mechanical states, and that's called a density operator. So far, are there any questions, or do people feel pretty clear so far? Great. So let's think of it. Let's go back to measuring our probability S, and let's generalize and say I have states psi j, all of probabilities pj. And so, and these are just, I don't know which one I have. I could have this one with this probability, this one with this probability. And we'd like to understand, how can I calculate the expectation value of any measurement? And so, like before, we'd say it should just be the weighted average of what you get if you're in any of the individual states. We can massage this a little bit though, and exercise to the viewer. This is equivalent to actually writing the trace of S of psi j, where this is the projector on state j. So we can actually rewrite this as S of pj sum over states psi j. And so now we've isolated out S, and we have something, some matrix or some operator that depends only on the states I'm putting into my ensemble. So this looks useful. Let's give it a name. We'll call it the density operator rho. And so suddenly, we've transformed this issue of I have a bunch of state vectors with certain probabilities to I just have a single matrix or single operator. And that is a completely equivalent description. And that's going to be how we talk about systems in the open quantum world. Just maybe a brief reminder, if you haven't seen it before, if I have, say, a projection state, if I have like a projection operator on the state ij, you can think of that, if we're in the basis, if these are basis elements, you can think of this as just being the matrix where row entry I and column entry j are 1, and then everything else is a lot of zeros. So really, you can just kind of read off. If I want to think of a density operator as a matrix instead of as an abstract operator, I can just write it out in this matrix form if you wish. And so now kind of one interesting thing you would notice right away is that somehow I've gone from, in a state vector description, you have n inputs or n variables, because in an n-dimensional system, you just have to say, what's this coefficient for all the basis elements. But if you've gone from a vector to a matrix, you've gone from n to n squared pieces of data. So that should suggest that an open system, or any mixed state as we call it, these probabilistic mixtures, has more freedom than a pure state, which should make sense because you can include pure states as examples of mixed states, but not the other way around. But more generally, from a dynamical point of view, that extra data of basically those off-diagonal entries are going to matter when we're thinking about how do we study the behavior of such a system. And to kind of see what I mean, we can think about the examples we were talking about earlier. So let's go back to the two superposition system before, where we had one state was this psi1 plus psi2 over root 2. Now this is a pure state, but you can think of it as a mixed state where you have a 100% probability of being in this state. you can work out that the density operator for this, written in the basis of psi1, psi2, would just be 1/2 and then all ones. On the other hand, and so that was our putative idea of maybe this is what we want to describe a system by. But the actual right answer we found was 50% being in this one, and then 50% in the other one. In this case, the density operator would just be 1/2 of psi1 plus half psi2, and that actually ends up just being 1/2 1 1 0 0. And so what we kind of said before was that essence of the difference between these two states was that in this one, this quantum superposition, you had interference effects between the two parts of superposition. In this one, because it's just a classical mixture, you don't have the superposition effects, and suddenly it's just like classical probability. You just take the average of everything for the individual states. And so you can also see this in the actual mathematical or density operator description, because if we just have this purely incoherent mixture of states, there's no off-diagonal entries in the matrix, and we just can read off that diagonal entry 1 has value 1/2, diagonal entry 2 has value 1/2. That ends up meaning, if you work through the definitions, that you have a 50% chance of being in state 1, a 50% chance of being in state 2. On the other hand, when you have these non-zero off-diagonal entries, that is how quantum interference, quantum coherence manifests itself in this new language. Because if you think about it, let's say you try to measure any observable, we saw before that the expectation value of a state of S becomes a trace of S in rho. Suddenly, when you're calculating out that trace, these off-diagonal entries come into play. Now that's how interference manifests itself. And if you try to change to a different basis, the interference effects will show up again. And so this should kind of give a bit of a paradigm that the physical interpretation of a density operator is you have n entries going down the diagonal, which are kind of like the coefficients of a vector, of the state vector, where it would just tell you what's the probability of being in this state. On the other hand, this new data we put in, this new data we have of these off-diagonal coherences, they tell us essentially how quantum is our mixture. How much quantum superposition is there, or is it just purely classical mixture in the sense that there's no superposition. And so when we're thinking about how dynamics of a open quantum system work, we're going to have to not only think about how does the population of a state evolve, which would tell me how fast is my atom decaying from excited to ground state, but also what do these coherences do? Maybe there are some interesting effects related to, does the coherence affect a population in evolution, vice versa? And that's going to actually become a big idea as we go. So now we've set up kind of the language of how we want to think about quantum systems evolving as these density operators. Let's try to think about how evolution actually occurs. And so there's a couple ways to do this. There's a more formal approach where, remember, at the end of the day, our goal is to describe how a system and environment evolve, but then only care about the system itself. So what you could do is you could ask, well, let's say I have a state for the system plus environment. I evolved that in time under the usual Schrodinger equation, and so I get the system and environment at a later time. From there, I could extract the density operator for the system, call it rho s of t. That's one way to go about it. And then what you could do is you could ask, how does this translate into a differential equation for rho of s? Because there's an operation called the partial trace, which I'm not going to go in detail on, but it's a systematic way to get from a system and environment to just a system density operator. So in principle, what you could do is you could say, well, I know how this thing evolves. I know how to extract information out of it. Then let me just get a derivative of rho dot by just essentially differentiating this whole thing and tracing over that. So the nice thing about that is that would actually allow you to understand how exactly system environment interactions come into play, because those would all be contained in this overall Hamiltonian H. That, of course, however, that takes a lot more work. That takes a lot of massaging of expressions, a lot of integrals that I don't really want to do today. So instead, I'd like to just think about qualitatively, what could evolution look like? What are we allowed to write down and be consistent with general expectations of quantum mechanics? So first of all, evolution should be linear. Because if I'm looking at a subsystem of an overall thing evolving by the Schrodinger equation, and the Schrodinger equation is linear, then the way the subsystem evolves should also be in a linear fashion. Sums should still evolve as sums, and so on. So if I demand linear dynamics, well, what data can I put in? I really want to have something that looks like the time derivative of rho at time t is some linear function of rho at time t. So what data do we have in rho? We have the populations, the coherences from before. So maybe as a first guess, we say, let's say everything just evolves as populations influenced by populations. So that's kind of an archetypal picture of, say, atomic decay. You have, yeah. Yes. So it's actually a linear map acting on linear maps. So this would be like an n the 4. The matrix is like by n squared entries. So you could write it out more explicitly, but I'm just, for now, it's just like it's some linear map on the space linear map. Yeah, yeah. So you can take the, so yeah, so this is the derivative in time. So really it's the component-wise time derivative of each entry, not the derivative. Yeah, it's not the derivative as a map on Rn. Yeah, good question, thanks. So great, so we've set up, so we say, okay, I will demand that, or I should expect that evolution should be linear. As a first guess, we could say, maybe all that matters is how populations evolve in time. And so we would write, for example, that the ith population, this II entry of rho, is sum over the, call them RII, RJJ, just some coefficients in front times the jth population of rho. And this is kind of just, this would just identify the rate of population transfer from state I, or from state J to state I. And so that's kind of a nice intuitive description that maybe matches what you think of phenomenologically when you think of, I have an atom that decays with some rate to, it decays with some rate k to a ground state, or it's undergoing radioactive decay. Those processes have these essentially these linear population equations where the linearity implies it goes like an exponential decay. You could try that. And so even with this, there's a lot of non-trivial things that can happen. But what you might want to say instead is, well, that's not the only linear thing I can write down. There might be something influencing some influence of the coherences. So maybe if we visualize it a little bit, let's say I have my state rho, this big matrix, and I have my entry rho II. Then what we said before is there should be some kind of population transfer to another state rho JJ. But in principle, because we just are looking for what possible linear equations they write down, we could also have influence from the off-diagonal entries, so these rho ij. And that doesn't have as immediate of a physical, or that's not as obvious physically, because traditionally when we think of these rate processes, we're thinking of, well, state I converts to state j with this rate. But now we're realizing that this quantumness, or this quantum superposition between them, as expressed by the coherence, can also affect their evolution. So mathematically, of course, that would just mean we have to generalize our equation to include the off-diagonal terms. So I could generalize this instead of being ij, ii to ij. I could just say the ij entry of the density operator evolves with some coefficients times all the other entries of the density operator. And so you might say, okay, well now what can I do with this? Well, one thing is suddenly now you've opened up more ways for population to transfer through the system. So in one regime, if things are very, very coherent, which means that these off-diagonals are quite large, quite comparable to the populations, you can expect that that will lead to very different dynamics than just pure population transfer. And so you actually see this in experiment. You see things like coherent oscillations and this sort of thing that are very much quantum in that they could not be described by these just classical rate equations. But once you account for the way superposition works, you can rationalize how they behave. So in principle, this seems like it's the only thing I can write down that's linear in rho. But there's one more thing I can do, which is implicitly by writing this equation, I've assumed that the evolution of rho actually only depends on the value of rho at time t. And you'd say, well, of course it does. That's how all of physics looks, right? F equals ma. You only care about f and a at time t. Schrodinger's equation is always about time t. Pretty much every PDE, every dynamical equation you write down is always about what's happening at this time and this time alone. So it would seem physically that evolution should be constrained to depend only on this moment in time. But remember that there's an external environment surrounding our system. And that's going to actually mess things up a little bit for us. So as an example, imagine I just have an atom, and it's surrounded by this cavity that can support photon modes. And at some time t0, the atom emits a photon. So maybe it goes from excited state to ground state, emits a photon. And then at a later time t1, say this is a mirror, the photon actually bounces off the mirror and comes back, hits the atom, and excites it at time t1. That information that the photon is about to hit you at time t1 is not present in the state of rho itself, which would just be, well, it's just sitting there in the ground state after having emitted the photon. That information either requires a full description of the bath, which we don't want to do because we don't want to describe the fine-grained details, everything surrounding the system, or alternatively, we can view it as the system at time t naught, by merit of being excited, ends up influencing the system at time t1 because the photon emitted comes back and hits it again. So more generally, because the bath or the environment is influenced by the system, just as the system is influenced by the environment, the environment that the system sees in a moment is dependent on what the system did in the past to the environment. So actually, the most general physical thing we could write down would also include, let's see, I'm going to write it over here, would also include this memory term that describes how the system in the past influences the environment now, or the system now. So this is just, you could say you can integrate the system, if you wish, from infinite past to the present, and then the way that the past propagates to now is captured in what's called this memory kernel. And so you'd imagine that typically this k of t minus tau would tell you how much, if I have k of 3, it would say how much did the system 3 seconds ago affect the system now. So you generally expect that it's going to fall off somehow with time, because as you go later and later in time, the effect from earlier and earlier should sort of fall away. And so this kind of system that evolves not just from what the system looks like now, but also how it behaved in the past, is kind of the hallmark of an open system, because the laws of physics are about time at this time and this time alone, right? F equals ma, Schrodinger, these are all about this current time. But suddenly, when we reduce our description, we're forced to start considering how the system could actually backpropagate and affect itself in the future. And so this kind of system that does this is called non-Markovian. And that's, it's related to in like probability theory, and you have Markovian, non-Markovian processes and so on. So that's kind of complicated. That doesn't look so fun to solve. Like we could, in principle, solving rho dot of t equals r rho just means exponentiate. Yeah.
Either they're that, like rows are called data to one. What's the non-Markovian?
Yeah, so it's not exactly the same as like a Markovian, like a Markov. Yeah, it's not quite the same as that. It's just the terminology, meaning that the effect of the dynamics of the system at this time are not only dependent on what the system is doing right now, but also how it was in the past. Basically, you cannot. I think usually the language in like probability is like the next step. You cannot determine the probabilities from the current step. It also depends on what were the previous steps taken by the thing. Yeah. Differentiate this on both times. Yeah, you'd end up with d rho on both sides. Then you still have to integrate that over, and then you also have this derivative of this kernel. So I think it's not, yeah. Yeah.
So it has like a memory effect essentially.
Yeah, in principle, yes, because the bath serves as this memory carrier for the system. So, okay, yeah, that's not fun to solve because integral differential equations are generally quite difficult to solve. And even writing down a formal solution, not so fun. So what we can do is we can say, how does this memory kernel behave? When can we ignore it? And so the example I had over here is very extreme, where I have kind of a small cavity so that when I emit this photon, the environment looks very, very different. Because if there was nothing and now there's suddenly something, that's kind of as big of a difference as you can get. But you can imagine instead, let's say this is already filled with photons, or it's so that adding one more doesn't actually really do anything. So if I have this very, very big environment, you can imagine that memory effects are going to start to become very, very small. So in that case, generally the intuition is, though not always true, but typically the larger environments lead to very, very small, very, very short-lived memory kernels. So in the limit of a infinite bath with very, very weak coupling in the system, you can actually often ignore this non-Markovian term. And in that regime, you do end up returning to this picture of just this classical rate process of the way the entries evolve in time are just some linear function of what they are right now. And that's what we probably would intuitively expect if we're trying to investigate what the physics should look like without any other input. So yeah, that's kind of that. And so yeah, you can actually go through and find more formal expressions for what does R look like, how does that R depend on system environment interactions, what does K look like, how does K decay, and so on by doing more formal theory. But the goal today is really just see what are the big picture of this evolution. So what I would like to do is think about a couple interesting setups, a couple maybe extreme cases. Because so far we haven't actually done any physics. I think we've just been setting up and musing over what the potential dynamics possibly looking like. I'd like to actually consider one example of a process. So we said before that generally, so the first question to ask, I guess, would be, what would we intuitively expect the system to evolve like for a long time? Because especially if you're interested in a lot of chemical processes that are occurring over larger than atomic timescales, the thing you're observing is going to be what happens in the long time steady state regime, like chemical reaction yields, these sorts of things that aren't happening on the nanosecond scale. So the first question you can ask is, intuitively, where's the system going to go over time? For example, if I start with some initial state rho naught, and I evolve it to rho at, I take t to infinity, I see where it goes. What's that going to look like? Are there some general features we can expect to see? And so first of all, we could say, oh, those coherences from before were kind of weird. They kind of gave some non-intuitive, non-classical behavior. Can we say anything about how they evolve? And if you remember, that example we had before where you had the absence of coherence and the presence of entanglement versus the presence of coherence in a pure state, what we saw was that coherence is kind of generally killed off by interaction and evolution because you're letting it evolve for longer and longer in time. So often, not always true, but generally often, if you have a system at least weakly interacting the bath, its steady state will look like something like P1 to Pn, and then all zeros on the off diagonals, at least in the energy eigenbasis, to good approximation. In truth, there always are some coherences, but they're negligible enough that we can effectively ignore them. And so in this regime, it's just because the system's evolved for a long time, it's been kicked around by the bath for a very, very long time. So any initial coherence presence in the system is just completely dissipated away. And if you like building quantum computers, this is quite a problem because quantum computing is built upon entanglement, coherence, superposition, these sorts of very quantum mechanical features. And yet, we've said that if we let a system go on for long enough, it becomes devoid of quantum features and is just this mixture of eigenstate 1 with probability P1 to eigenstate n probability Pn, no kind of quantumness to that. So that's you might look at that and say, oh, that's a bit of a danger for building quantum computers. But alternatively, you can say that's kind of interesting because this looks like statistical mechanics. Because it maybe if you've done some statistical mechanics, you know that, for example, in the canonical ensemble, if you have a system, it's kind of like one of the big paradigms in StatMech is if you have a system here and it's interacting with some big heat bath at temperature T, then you know that in the thermal equilibrium, the probabilities of being in the state J should be as e to the minus beta Ej over the partition function, just to normalize it. And this is kind of the same thing as in when you talk about Maxwell-Boltzmann speed distributions, all these kind of thermal distributions that you know that somehow when you let something talk to a heat bath for long enough, it goes to one of these statistical ensembles. But that's actually the same thing as what we've written over here, because this is saying that the probability of having eigenstate Pj is just e to the minus beta h. And then the way you do averages in StatMech is you'd say an average is just going to be this sum over Pj and then average in state J. In particular, there's nothing quantum mechanical about this. So when you talk about StatMech, you are just saying, you really are considering this kind of classical distribution where there's no superposition, there's no coherence. Everything is just take it at face value of I have this state with this probability, this state with this probability, and so I can just take weighted averages. And so we can actually kind of see how that's born from open quantum systems by realizing that by merit of the way the system and the bath entangle and you lose quantum effects, quantum coherence, you actually start to see StatMech emerge from there. And so you might even say, well, how do I get these particular coefficients? It turns out that actually if you go through the theory of how you get these R's, or these rate matrices, or these rate coefficients, in some at least in certain theories, in particular what's called Redfield theory, you'll find that the ratio, the rates from state I to state J actually take the form of basically this exponential of the energy gap. Now let's see if I the other way around. But that just says it's the ratio of these two exponential refactors. So what that means is if you actually were to try putting in this canonical ensemble and you know the rates satisfy what's called this detailed balance relation, you actually do find that the steady state will be the canonical ensemble. And so I've always found that very nice because I thought that when StatMech is first introduced as this, I always thought it was very esoteric or very weird that we suddenly go to these ensembles. I didn't really see where they came from. So that's why I've always liked the open picture, opus's point of view, which is that a statistical ensemble is just the result of time evolution plus entanglement and decoherence, which takes you from this well-defined, maybe initially coherent state towards the statistical ensemble. But we've actually done a little more work than just getting steady states. Because the nice thing is we have a dynamical framework. We have dynamics and we can derive dynamics. So we could also start to do is we could ask for more interesting situations, just a system interacting with a single bath. We could imagine, for example, a system can talk to two things, environment 1, environment 2, with temperatures T1 and T2. And let's say those temperatures are not equal. And so intuitively you say, well, now there's going to be some kind of heat flux from, let's say T2 is, let's say this bath is colder than this one. There should be some flux of heat mediated by the system as it goes from hot to cold. And so you can ask, maybe now it's not just a canonical ensemble anymore. It's not this equilibrium ensemble, but instead it's something that would characterize the flux and it would show how energy can actually be carried from one end to the other. And so you can kind of do the same thing. You can imagine you set up your dynamics, you evolve them in time as far as you want to the steady state, and you end up with, instead of the canonical ensemble, what's known as a non-equilibrium steady state. And so non-equilibrium just means that there are these permanent fluxes essentially going through. You're always, because to have flux, you need something driving a flux. So it tells you that there's something mediating or driving that, and that exactly is this temperature gradient. But this you wouldn't have predicted from just canonical ensemble alone, because you had no way of understanding how dynamics and system evolution are modified by more complicated scenarios than just, say, system with a single heat bath. And so you might actually ask, okay, this seems a little bit contrived, right? What can I do beyond just, does this actually occur in the real world? Does this just kind of, I have a lab set up with one thing with a hot end and a cold end on the rod, and I let the heat conduct along the rod? It turns out, yeah, this is actually a very common situation. That's kind of what I want to wrap up with. And this is when I need to actually look at what the structure is of this molecule. So there's in your eye relies on photochemistry and photochemical reactions to help you see. In particular, when light comes and hits your eye, there's a molecule called retinol that gets hit by the photon and then undergoes some quantum mechanical process, and really a bond just flips from cis to trans. So what that looks like, you have some complex molecule with something over here and something over here, and then there's some bond, some rigid bond. When you hit that with a photon, you have enough energy for the bond to flip, and you end up with this reconfigured molecule. And so but of course, you want this reaction to happen fairly often, because if it's the first step of vision, it better be a pretty reliable process. Otherwise, you aren't going to be able to see. And so you might want to study, say, what's the actual photochemistry or photophysics of how this goes from cis to trans. For example, if you were to draw out like potential energy surfaces, what path does the state take? Does the wave packet just get hit up from one to the other and then propagate down, and so on? And you can ask, how is this optimized? Is this the best it can be in nature? Or are there better ways? Because nature is generally really good about driving these processes. So you'd want to study this as an open system, because it's not just an isolated retinol molecule. It's a molecule that's being hit not only with the sun and its photons, but also it's also being bombarded constantly by the surrounding solvent and protein molecules. So in this case, really, you do have a non-equilibrium steady state set up, because on one hand, one of your baths is the sun at 5,800 Kelvin, and the other is your body, or the protein surrounding it. And I'm going to hope your body is not at 5,800 Kelvin, so that indeed is at a lower temperature, 310 Kelvin. And so you can study, how does the system evolve under, one, being hit constantly by these vibrations in the protein, two, being excited by the sun, and how does it evolve later in time? And in particular, what does the steady state of this system look like? Because in the steady state, that would tell you what % of the molecule reacts to become trans, what say cis, and you want a big yield so you can actually have a reliable vision process. And so this is kind of some of the research that I'm interested in and my group's interested in. And so there's lots of great things, lots of very interesting effects that you would expect just from equilibrium physics that you can kind of find once you kind of prod things into this non-equilibrium realm. So I think it's with that I want to kind of finish and say, what have we done today? Well, we've said that hopefully I've convinced you that this open system paradigm, that you don't want to study the entire system, but rather a smaller subsystem, is actually not a foreign concept. You've thought of that as long as you know what friction is, which probably you've been looking at as long as you've been alive. But the big quantum issue was entanglement messes things up. Entanglement says it's not as simple as just ignore everything and use effective Hamiltonians, you have to actually go to this probabilistic density operator picture. And then we thought about how do we look at dynamics, what are the possible forms they can take, and more generally, what kind of physics actually shows up once you start to consider this open realm. So with that, I want to end. I will, if anyone's interested, I can give them a lot more references on where to go. If you want to learn more about this, just come talk to me after. And hopefully, if anyone has any questions, please feel free to ask now. And thanks.
Right. Thank you so much for the great talk. Now we'll have some questions. Please feel free to take some cookies and tea.